Welcome, Isaac here. Today you'll learn about differentiable quantum circuits and functionalities built into PennyLane to facilitate differentiating quantum circuits. Specifically, we'll look at differentiation methods that are hardware compatible. We also recommend that you check out our video on how to optimize circuits in PennyLane as well. If you're watching this video, chances are you've heard of machine learning libraries like PyTorch, Keras, and TensorFlow. And the reason they became so popular was actually quite simple. Machine learning concepts in the scientific community and in industry were becoming more and more useful and interesting, but at the same time, the machine learning models being developed were becoming more and more complex. So these machine learning libraries give a nice platform and a solution for people to test, develop, and prototype really complex models that were modular and easy to write. To train machine learning models, we often fall back on gradient methods to update the parameters within the model, thereby necessitating that the software packages we use be differentiable. Quantum computing, quantum algorithms, and quantum machine learning are also becoming more and more popular. So naturally, a software package that can facilitate these needs in an analogous fashion, like the classical machine learning packages like PyTorch and TensorFlow and Keras, is needed. In comes PennyLane. Not only does PennyLane check these boxes, but it's developed with differentiability as a top priority. So in this video, we'll go over differentiation methods that are built into PennyLane with specific emphasis on hardware-compatible differentiation methods. Grab some coffee and let's dive in. Okay, and here we are on Xanadu Cloud in a notebook. And as always, we start by importing PennyLane as QML, and we're going to import PennyLane's wrap version of NumPy as well. And we're going to be printing a lot of floating point numbers today, so I figured it'd be nice to just set some print options to see numbers a little nicer. Next, we need a device and a circuit. Now, everything in this video will be hardware compatible, but let's just use the default qubit simulator here for convenience. And our circuit's going to have 2 qubits in it. So now let's actually create our QNode. So let's do @qml.qnode. We give it the device. We're going to call our quantum function circuit, and I'm going to give it some parameters that we'll want to differentiate over later. Our circuit's going to have 2 gates in it, the first being a poly Y rotation on the first qubit, where the rotation is given by the first element of this params variable. And the second gate is a poly X rotation on the second qubit, where the angle of rotation is given by the second index of params. And finally, it's going to return a measurement in the expectation value of the linear combination of the poly Z operator on the first qubit and on the second qubit. And just a quick sanity check, let's just make sure that our circuit's working for a given set of parameters. Nice. Now let's just briefly recall what a QNode is doing in PennyLane for a second. It's taking a quantum function that has gates and a measurement, and then all of that is joined with a device, either a simulator or real hardware. So in that sense, the device will definitely come into play when we start talking about taking derivatives of our quantum function on the device. To take that into account, when decorating your quantum function with @qml.qnode, you can also specify a keyword argument called diff method. And as the name suggests, this specifies the differentiation method that you want to employ whenever you ask PennyLane to take a gradient of your quantum function. Now, you don't have to specify what diff method is every single time you make a QNode. You can leave it out. What happens under the hood is PennyLane chooses the most performant differentiation method that's compatible with the device. We'll talk more about the diff method keyword argument later, but just keep this in mind for now. All right, now let's actually differentiate this thing. In PennyLane, there are several differentiation methods to choose from, 2 of which are hardware compatible. Those 2 methods are called the finite difference differentiation method and the parameter shift rule. We'll go through both in this video, but let's start with the finite difference gradient method. When you first learn about differentiation, you're probably exposed to first principles differentiation. And it basically says that the derivative of a function is given by the linear combination of the function evaluated at 2 infinitesimally close points divided by the infinitesimally close shift. Now, numerically, we can calculate this derivative by instead using a small but finite value of the shift, not infinitesimal. So let's see this in action with our circuit. And what we'll do is we'll create our own finite difference gradient function for illustrative purposes. And then we'll use what's built into PennyLane and compare the 2. Okay, so let's call our custom finite difference gradient function myFiniteDiff grad, and we have to give it the parameters that we want to differentiate with respect to. And for this not infinitesimal but very small value h, let's just set it to 10 to the minus 7. So to calculate the gradient, we need to loop over every single parameter that we want to differentiate with respect to, calculate each partial derivative, and collect all those partial derivatives into one object that is the gradient. So let's collect all of our partial derivatives in a thing called gradient. And then let's loop over our parameters. So for I in range len params, Now first, let's calculate the term that involves a circuit evaluation where h has been added to the parameter. So let's increase our parameter by h. And then with the circuit evaluated at the parameter plus h, we can put this into the gradient for now. Next, we need to evaluate the term where the circuit is evaluated at the parameter minus h. So since we just changed our parameter by plus h, to get a net effect of minus h, we need to subtract 2h from our parameter. Now we can calculate the second term in our linear combination that involves a circuit evaluation. So we just do gradient of I minus equals circuit of params. Okay, and then lastly, we need to divide this by 2 times h. And then you'll notice here that if we stop, our parameter has been changed in total by minus h. So we just need to undo that at the end. Okay, and then in doing this for every single parameter, we will have calculated the partial derivative of our quantum function with respect to each parameter. And so all we need to do is just return the full gradient. All right, now we're ready to do this with PennyLane exclusively. So we need to create another QNode. So at qml.qnode, we give it the device. And this is where we're going to specify that diff method keyword argument I was speaking about earlier. And to specify to PennyLane that whenever we want to take a gradient of this particular quantum function that we're about to create using the finite difference gradient method, I have to specify diff method equals finite-diff. Okay, and then we're going to call this quantum function circuit finite-diff. And it's going to be the same circuit as before with the same gates and parameters and returning the same measurement. So we've defined our own finite difference gradient function, and we've done something in PennyLane exclusively. So let's just compare the two. Let's arbitrarily define what the parameters are that we want to differentiate with respect to. And to make PennyLane see that these are actually parameters that we do want to differentiate over, we have to specify within this definition of a NumPy array requires grad equals true. So let's print our finite difference gradient function with respect to these parameters. And then to do the same in PennyLane, there's a function called qml.grad, which basically takes in a QNode and returns the gradient function of that QNode. So our QNode is called circuit finite-diff, and we want to evaluate the gradient function at these particular parameters. And running this, you can see that our finite difference gradient function and what's built into PennyLane are super close. They're the same up to about 5 or 6 digits of precision. And this illustrates a problem with the finite difference gradient method. The finite difference gradient method is an approximation to the actual gradient, and the approximation's accuracy depends on how small this value h is. The smaller we make it, the more accurate our approximation is. Ideally, we would want an exact gradient. And that's not the only issue with the finite difference gradient method. If we want to evaluate a finite difference gradient on a near-term device that's really noisy, say, changing our parameters by this really small amount might get lost in the noise, so to speak. That being said, the finite difference gradient method is actually hardware compatible. To compute one partial derivative, we just need to call the circuit twice at different parameter values. But it would be nice to have a gradient method that's hardware compatible, yes, doesn't get lost in the noise, and is exact. This brings us to the parameter shift rule. A team of researchers, including many here at Xanadu, showed that with some very reasonable assumptions on the gates in our circuit, partial derivatives can be evaluated exactly with the formula that's on the screen. Now, this might look a little messy, but it simplifies quite nicely actually when the gates in our circuit are, say, the polyrotation gates, which is what we have in our case. In any case, the parameter shift rule basically says that partial derivatives of our quantum circuit can be computed with linear combinations of circuit evaluations at shifted parameters. So again, we can ask real hardware to do a lot of heavy lifting here, and this shift S doesn't have to be very small like in the finite difference differentiation method, so we won't get lost in the noise. So let's proceed like we did for the finite difference differentiation method. We're going to create our own parameter shift rule function for illustrative purposes, and then we'll use PennyLane exclusively. So let's call our parameter shift rule function my parameter shift grad. And again, we have to give it the parameters we want to differentiate over. And for this shift value s, let's give it a default value of pi over 3, which definitely isn't small like 10 to the minus 7. And because the parameter shift rule for the polyrotation gates is eerily similar to the finite difference differentiation method, our parameter shift rule function is going to look very similar to our finite difference differentiation function. We loop over our parameters, we shift our parameters in the positive direction first, and we evaluate our circuit at that positively shifted parameter. Next, we shift our parameters by minus s and evaluate our circuit at that shifted parameter. The factor we divide by is a little different. Here it's 2 times the sign of our shift value, s. And then lastly, we just have to reset our parameter like we did before with the finite difference differentiation function. We've shifted it by plus s, then minus 2s, bringing us to a total of minus s, and we just have to undo that. Doing this for every parameter gives us the gradient of our quantum circuit, so we just return the gradient. Now to do this in PennyLane exclusively, we again create another QNode where we have to specify this diff method keyword argument again, and the string that we give it to specify that we want to use the parameter shift rule every time we take a gradient of our quantum function that we're about to define is parameter dash shift. Let's call this quantum function circuit parameter shift. Again, we give it the parameters. And as before, we're going to use the same gates in our circuit and return the same exact measurement. All right, so let's print off what our parameter shift rule function gives us. And then again, using PennyLane, we have to call this qml.grad function. It's going to take the QNode, so circuit underscore parameter shift. And again, that returns the gradient function. So we have to evaluate that function at our given parameters. And when we run this, you can see that both results are exactly the same, right up to the 10 digits of precision that we're printing out. And again, this is because the parameter shift rule is exact. Now, it is worth mentioning that although the parameter shift rule function we created here is relatively simple, this doesn't generalize to general gate sets. So we definitely recommend that if you do want to use the parameter shift rule for your differentiation method, that you specify diff method equals parameter shift like we have here. Not only because you don't have to worry about generalizing to different gate sets that aren't the polyrotation gates, say, but also because our developers work extremely hard to make sure that PennyLane's implementation of the parameter shift rule is very fast and efficient. All right, and that'll do it for today's video. You now have a very good understanding of two important hardware-compatible differentiation methods built into PennyLane in the finite difference differentiation method and the parameter shift rule. You can find out more about quantum differentiation on our website. If you enjoyed this video, be sure to leave a thumbs up and make sure to subscribe for more quantum computing content from Xanadu.